In this video, I'm going to be going over isotopes. So take a few moments here to pause the video and answer these review questions, and then we'll go over it with each other. All right, so what gives mass to an atom? Well, you should have said the protons and neutrons. Ignore the red and black. So you're right, protons and neutrons both have a mass of 1 AMU each. And while electrons have some mass, right, their mass is like 0.00005 AMU. So that's barely anything. So that's why I don't really consider electrons attributing to the mass of the atom compared to the protons and neutrons. All right, so which subatomic particles can vary within the same element? Electrons and neutrons can. So protons don't vary because protons are what defines what the element is. So carbon is element 6. It has 6 protons. That is what carbon is. It has 6 protons. That's different than nitrogen with 7 protons. So protons define what the element is. Electrons and neutrons can vary. And we'll talk about how electrons vary in another unit or so. Today we're really going to look at these neutrons varying. And then how do we date biological fossils? We use carbon dating. And I bring this up again because remember in the video we watched about carbon dating, they talked about carbon 12, carbon 13, carbon 14, and so that's going to be coming up again today now, what those numbers mean after that. All right, so this takes us to atomic mass. So how do we find it for an element? Well, we look at the block on the periodic table. So this number down here is telling us the atomic mass of iron. And so that is going to give us the information we need to do like the molar math problems. And it's looking at a whole sample of it. Now, why isn't this a whole number? It's because it's an average. So, protons and neutrons both have a mass of 1 AMU each. So if we're not seeing like a perfect whole number, that means that we're seeing an average of all the different isotopes out there. And again, why are there differences in mass of each element? Because their number of neutrons can vary. So these neutrons can vary, attributing to different masses, and that means that we then need an average. Right. So this takes us to isotopes. The definition of isotopes are atoms of the same element with different masses due to different numbers of neutrons. So that's what we see here. So we see the 3 different carbons. We have carbon 12, carbon 13, carbon 14. The numbers listed here, these percentages, are telling us the abundance because not all isotopes come in the same abundance because some are less stable than others, some form through radioactive decay. There's a lot of weird things that can go on with it. So carbon 12 is the most abundant type of carbon, with 98.9% of carbons being carbon 12. Carbon 13 is 1.1%, and then carbon 14 is less than 0.1%. Now notice the protons are all the same. They all have 6 protons. Again, that's because it's carbon, right? Carbon always has 6 protons. That defines carbon as 6 protons. And now we see the neutrons are changing. So carbon 12 has 6 neutrons, right? 6 plus 6 is 12. Carbon 13 has 7 neutrons, 6 plus 7 is 13. And carbon 14 has 8 neutrons, 6 plus 8 is 14, right? So these are adding up to what we see here as the mass. So how do we identify the isotope? When we want to discuss a specific isotope, we use the mass, not the number of neutrons. You can always back work to the number of neutrons because if you know the mass and the element, you're going to know the number of protons, so then you can go back to what the neutrons are. We can use the hyphen notation. So that's where we use the names dash mass. This is how we verbally describe it. So when we were talking in the last slide here about carbon 12, carbon 13, carbon 14, that means then, those are describing the masses, and that's how we kind of talk about it. All right, so we have an isotope of hydrogen with 1 proton and 1 neutron. What would we call it? Hopefully you got hydrogen 2. So our hydrogen, that's element 1, so that means it has 1 proton. And so if we have 1 neutron then, 1 plus 1 is 2. So hydrogen 2. Right. So now what about the nuclide notation? This is where in superscript, so this is like the normal script line, right? So super means above. So on the left side in superscript, we put the mass and then the symbol. Sometimes down here in subscript, you will also get the element's number or the atomic number for that element. Both are correct. I just find like just having the mass is more important because again, you can always look up what the element is. So having the atomic number isn't as important. So we tend to use this if we're writing it so that the isotope matters in a chemical reaction. And you'll be practicing this next class with radioactive isotopes. So for example here, if we have an isotope of chlorine that has 19 neutrons, how would we write it in nuclide notation? Well, if you look this up on the periodic table, chlorine is element 17. So that means it has 17 protons. 17 plus 19 is 36. So we do 36 in the upper left corner, Cl. All right. So again, so that's isotopes, right? And there's a variety of isotopes. So that means we now need to know how we find this average mass. And so we're going to talk about taking averages. So we're going to find out the average age of the class, and I'm going to do somewhat from memory from yesterday's class. So there's no 13-year-olds, 1 14-year-old, 8 15-year-olds, 16 16-year-olds, and 1 17-year-old. So is our average going to be 15 and a half? It might be close because, right, we have a lot of 16-year-olds and a lot of 15-year-olds, but it shouldn't be exactly, it might not necessarily be exactly that, right? That would be more like the median age where you look at like what's the middle point between our numbers. Now to take the average, we need to account for how many of each people are in each age group. So what we would do is we'd say, okay, 14 times 1 plus 15 times 8, because there's 8 people with it, 16 times 16 plus 17 times 1. Now what do we divide this by? Remember, averages have to be divided by the whole. So we want to divide by 4. We're going to divide by 9, 10, 26. For those of you wondering what I just did, I just added up these values here, right? That's the total number of people. If I do this on the calculator on the iPad, the screencasting is going to die. So I'm doing this on a separate calculator. So I'm going to do 14 times 1 plus 15 times 8 plus 16 times 6. This isn't working right. Sorry. Doing this on a old calculator. Okay. So we're going to do 14 plus 15 times 8 plus 16 times 16 plus 17. And then I hit enter. So I do that top line first, and then I divide by the total number of people. And we get 15.765, but I'm going to round to 7. Right? So that would be the average age of this class sample here. So, right, we should expect for it to be between 15 and 16 because that's where most of the students are in age. And it leans a little more towards 16 because there's more 16-year-olds than 15-year-olds. All right, so now let's do this for finding the average atomic mass of an element. So this is the equation we use. So you're going to have a mass of the first isotope or isotope A multiplied by its percent abundance, plus the mass of B times its percent abundance, plus C's mass times its percent abundance. And you can go on. You can have D, E, F, G, however many isotopes you're looking at. Also, you might only have 2 isotopes, so you would cut out C there, right? But that's kind of the idea. That's how you would do that top line. And then notice how we have percentages here. So because we have percentages, we're going to divide by 100. So let's do this here. So we have magnesium 24 with a percent abundance of 78.7%. Magnesium 25 with a percent abundance of 10.13, and magnesium 26 with a percent abundance of 11.17. So how do we know the masses here? Hopefully you said to yourself, they're given to them in the name, right? So these are the masses of those isotopes. So to solve for this, we're going to do 24 times 78.7. And I'm going to keep the percent there because that reminds me that I need to divide by 100 because my total percentage should always add to 100. So here I'm taking the masses and multiplying by their percent abundance. And then I'm going to divide by 100 in the end. So again, I don't have, if I use the calculator on the iPad, it's going to screw up the screen recording. So I'm doing this on a separate calculator. So we're doing 24 times 78.7 plus 25 times 10.13 plus 26 times 11.17. Now I'm going to divide by 100. I might have hit something wrong because my answer is not being correct here. Definitely should have 22, so sorry. So it should be like 24.3 something. I want to have the correct answer though for you, so 1 second. Now we have the right one. So it's 24.3143, and the units here would be AMU. Now, why am I not rounding like we normally round? Because with this average, you kind of want to give more information than just like perfect whole numbers. We do want to go a little further out. I would say if you want to round, maybe the hundredths place would be a good place to round because that's generally where we want to have our atomic masses at. So more information here is fine because we're looking at that average mass. All right, so now you give this a try here. So you can pause this and solve it. And I'm going to give you the answer in a moment. All right, so you should get 152.04 AMU. All right, so that is averages and isotopes.